Hi, my name is Alicia.
And my name is Prachi.
And in this video, we're going to be teaching you all about the intersection of lines and planes.
From section 8.5. In 3 space, a line can be defined by a vector equation in the form r equals to r0 plus tm, where the domain is ter, where r is a position vector to any unknown point on the line, r0 is a position vector to any known point on the line, and m is a direction vector parallel to the line such that the coordinates are m1, m2, and m3.
In 3 space, a line can also be defined by a parametric equation. Okay, so x equals x0 plus tm1, y equals to y0 plus tm2, and z equals to z0 plus tm3. So you're probably wondering what a plane is. Well, a plane is a two-dimensional flat surface that extends indefinitely far in all directions. The scalar equation of a line defines a plane. So as you can see, ax plus by plus cz plus d is equal to 0. Sometimes it can also be written as ax plus by plus cz is equal to negative d.
When a line and a plane intersect, there are 3 possibilities. The first possibility is that if the line and the plane intersect at exactly one point, there is exactly one solution.
So if you don't understand, think of this analogy. Imagine shooting an arrow from any elevated hill, so at any certain angle, or from any direction, as long as it is not parallel to the plane.
The second possibility is if the line lies on the plane, then every single point on the line intersects the plane and there are an infinite amount of solutions.
So if you don't get this one, think of this analogy. After shooting all of those arrows, you're really tired, so you're going to lie on the floor. The floor is the plane and you are the line. Your whole body is touching the floor. So that line is touching all parts of the plane.
Third possibility is if the line is parallel to the plane. Then the line and the plane do not intersect at all, and so there are no solutions.
So if you don't get this one, think of this analogy. So after all that napping, you had a sore back. So you decided to sleep on the park bench. The park bench is outside of the field. So you are now sleeping on something that is parallel but away from the field. So you are exactly like this possibility. You are parallel to the plane, but not touching the plane. Therefore, there is no solution of intersection. Alrighty, so now on to practice problems. So for example number 1, we have determine if the line and the plane intersect. So we're given 2 equations. This symbol here represents the plane, not pi. So plane 1 is equal to 9x plus 13y minus 2z is equal to 29. Now the line is represented by L1, and we get x equals to 5 plus 2t, y equals to negative 5 minus 5t, and z equals to 2 plus 3t. So in order to figure this out, this is very simple. All we have to do is sub the line equation into the scalar equation of the plane. So we're going to get 5 plus 2t plus 13, negative 5 minus 5t, minus 2 plus 3t, and all of it is going to equal to 29. This is very simple substitution. Now all we have to do is expand, and when we expand, we're going to get negative 53t is equal to 53. Now all we have to do is solve for t. Very simple. So t is going to give us negative 1. Okay, so that was step 1. Now step 2, we need to find the coordinates of that intersection of the plane. So all we have to do is sub our t value that we have found back into the line equation, which is the parametric equations. So we're going to get x equals to 5 plus 2 negative 1. Y is going to equal to negative 5 minus 5 times negative 1. And then z is going to equal to 2 plus 3t, and that's going to be negative 1. And our coordinates are going to be 3, 0, and -1. So this is our one intersection. Now since we only had one t value, that means that there is only one intersection between the line and the plane. So that makes sense. That's why we only get one set of coordinates of the intersection.
In this practice problem, we have to determine if the given line intersects the plane, and we are going to do this without doing much calculations. So the equation of the line is given right here, and the equation of the plane is given right here. The direction vector of the line is 3, 2, and 1. So this is our direction vector portion. And the normal vector of the plane is n is equal to 3, -1, and 1. And I got this coordinate from the x value of 3, the y value of -1, and the z value of 1. So now we're going to find the dot product of n and the direction vector of the line, and to see if they are perpendicular. So let's do this. So we're going to get, 3 times 3 plus 2 times -1 plus 1 times 1. And now this is going to give us 8. And since the dot product is not 0, m and n are not perpendicular, and the line and the plane are not parallel, so they must intersect. Now the third practice problem we're going to be doing is determining the Cartesian equation of the plane containing the points A, which has coordinates -1, 2, and 5, B, which has coordinates 3, 2, and 4, and C, which has coordinates -2, -3, and 6. So for this question, we're going to be finding the cross product between vectors AB and AC, and as determining the cross product between the two vectors determines the normal to this plane. So first, before we do that, let's find the direction vectors AB and AC. To find the direction vector AB, we're going to subtract the coordinates of point B by vector A. So vector AB will be 3 minus -1, which will be our I coordinate, 2 minus 2, which will be our j coordinate, and 4 minus 5, which will be our k coordinate. So vector AB is going to be equal to the coordinates 4, 0, and -1. Now we're going to do the same thing for vector AC. So in order to find vector AC, we're going to subtract the coordinates of point C by point A. So this will give us to be -2 minus -1 for our I coordinate, -3 minus -2 for our j coordinate, and 6 minus 5 for our k coordinate. So vector AC is going to be -1, -5, and 1 as the coordinate. Now that we found our vectors AB and AC, we're going to be finding the cross products of these direction vectors. So we're going to be doing our I, J, K table, and we're going to be writing out the coordinates of each vector. So the cross product of AB and AC will be like this. So we'd have 0 times 1 minus -1 times -5 for our I coordinate. Then we'd have -1 times -1 minus 4 times 1 for our j coordinate, and 4 times -5 minus 0 times -1 for our k coordinate. So this in turn, the cross product of AB and AC will give us the coordinates -5, -3, and -20. We can also simplify this coordinate by taking the -1 outside of it, and we can write this as 5, 3, and 20. So in order to find the Cartesian equation of the plane, we're going to assume point P is going to be making a vector with coordinate A. So let point P have the coordinates x, y, and z. So AP in turn should be equal to x plus 1 as your I coordinate, y minus 2 as your j coordinate and z minus 5 as your k coordinate. So now that we've gotten AP, we can find the equation of the plane, because since a normal to the plane would be this vector right here, the cross product of AB and AC, the dot product of the dot product of the cross product of AB and AC and the vector AP should be equal to 0. So this will let us find the final equation of the plane. So we would solve this by doing the dot product of both. So this is how you would solve it. So the simplified equation, when we expand this, we will get 5x plus 5 plus 3y minus 6 plus 20z minus 100 is equal to 0. And now when we simplify this equation further, the equation of the plane that we will get is 5x plus 3y plus 20z minus 101 is equal to 0. And now we have our equation of the plane. Okay, now moving on to some application problems. So as you can see here, here's one question. A runway is on the plane with the equation x minus 2y plus 3z plus 4 equals 0. The line that will intersect the runway is formed by the descending of an airplane with the parametric equations of x minus 4 over 2, y plus 2 over 6, and negative z minus 6 over 3. Find the angle between the intersection of the runway with the airplane. So to solve this, we will need a direction vector. Let's call that direction vector S. We can find a direction vector from our parametric equation from our line. So our direction vector, the coordinates of it would be 2, 6, and negative 3. We also need a normal vector to find the angle between the airplane and the ground. So let's call our normal vector n. And our normal vector, we'll get the coordinates for the vector from the equation of the plane, which would be 1, negative 2, and 3, as you can see here. So the x-coordinate is 1, the y-coordinate is negative 2, and the z-coordinate is 3. So to find theta, we will use the equation sine theta is equal to the dot product between the direction vector s and the normal vector n divided by the magnitude of the direction vector times the magnitude of the normal vector. So this will give us sine theta is equal to 2 times 1 plus 6 times negative 2 plus negative 3 times 3, all of this divided by the square root of, as we're finding the magnitude of both vectors, 2 squared plus 6 squared plus negative 3 squared, and all of this will be multiplied by the square root of the normal vector. So it would be 1 squared plus negative 2 squared plus negative 3 squared. So now we'll have something for sine theta. It should be equal to 19 over 7 times root 14. We still need to find theta. So sine inverse of 19 over 7 times root 14 will give us theta. So theta is equal to 46.5 degrees. Therefore, the angle of intersection between the runway with the plane, the angle that it makes is 46.5 degrees.
Okay, so now to the next application question. John is going to play archery with his friend. He is standing at point 1, 0, negative 1. His target is on the plane 5x plus 4y plus 3z is equal to 1. Find the distance between John and his target. So now, what we have to do is find the distance equation. So they've given us a diagram, And as we can see here, P, our point, is here. We have an unknown point, Q, is here. And distance is obviously this vector right here between the plane and the point. So let's just call this vector V. So vector V is equal to distance. Now, we know V is projection of the vector PQ on the normal vector of the plane. So, our coordinates for our n vector are 5, 4, and 3, and we get this from the scalar equation of the plane. So x is 5, y is 4, and z is 3. So, to find distance, we need our distance equation, which is the magnitude of PQ dot product with n. So, it's going to look like this over the magnitude of n vector. So we have our distance equation, but we're just going to keep that aside for now, and we're going to go back to this point Q. So Q is an unknown point, so we want to find its coordinates on the plane, where it touches the plane. So to find this, we're going to set its x value equal to 0 and its y value equal to 0. So this, then we can solve the the z value. And to find the z value, we're just going to plug these into the plane equation. So it's 5 times 0 plus 4 times 0 plus 3z is equal to 1. And then we're going to get 0 plus 0 plus 3z is equal to 1. So z is going to equal to 1 over 3. Therefore, our coordinates for Q are going to be 0, 0, 1 over 3. So it's a good thing that we found our point Q, because we're going to need to form the vector PQ in order to find our distance. So vector PQ is going to equal to -1, 0, and 4 over 3. So all we have to do now is plug this into our distance formula. So we're going to get the dot product of PQ, so -1, 0, 4 over 3, dot product with 5, 4, 3 absolute values over the absolute value of the normal vector.
To find the dot product of points PQ times the normal divided by the normal. So the dot product would be this top line here, and we're going to divide that all by the magnitude of the vector, normal vector. So that would be 5 squared plus 4 squared plus 3 squared. So this in turn is going to give us -1 over root of 50, but since we want the absolute value, we're going to get the distance of 1 over square root of 50 as our answer. So that is the distance between John and the target, 1 over root 50.
So now moving on to the last and final application question. Amy says the plane and the line will be coincident. Jake says that they will not intersect at all. Prove who is right. And we are given the scalar equation of a plane and the vector equation of a line. So what we have to do first is turn this vector equation of the line into a parametric equation of the line. And this is simple by just joining the x coordinates with the x coordinates of each of these. So x is going to equal to -2 plus 3t. Y is going to equal to 4 plus 1t, and z is going to equal to 1 minus 1t. So next what we're going to do is sub each of these from the parametric equation into the scalar equation of our plane. So we're going to get 4 times negative 2 plus 3t minus 4 plus 1t minus 11 times 1 minus 1t. So now this whole thing is going to be set to 1 as our scalar equation is equal to 1. So we're just going to simply expand, and we're going to get negative 8 plus 12t minus 4 minus t plus 11 minus 11t is all going to be equal to 1. Now we're going to collect like terms. So we're going to get 12t minus t minus 11t minus 8 minus 4 plus 11 is all going to equal to 1. 0t, because these all cancel out, and minus 1, as negative 12 plus 11 is going to give us negative 1 is going to equal to 1.
0t is equal to 2, and t is equal to 2 over 0. So therefore, there are no values of t which make the equation true, since it becomes undefined. Therefore, there is no solution, and therefore Jake is correct. Problems. Pause the video and try them.